Hello everyone, can you hear me? Yeah, okay, thank you to be here. Tonight I'm going to talk about event-driven microservices. I will share with you the evolution of the HPC architecture and how we think and why we think that introducing stream and events can solve some of the problems that we have seen in the past. And I'm going to show you also some of the mistakes. I have to use, okay, right. Okay. I'm going to show you also some of the mistakes that we did in the past and the solution that we think can help us to solve these mistakes. So just a quick one about me. My name is Fabrizio Fortino, staff engineer here in this office for HPC Tech. Been in the software industry for more than 15 years now. In my spare time, I like to contribute to some open source project, but in fairness, I was a bit lazy in the last period, so I hope to go back soon and contributing more. So what this talk is about, I'm going to give you a quick overview of how our architecture evolved and why we choose to pick we picked Kafka to solve some of our problems. We are implementing right now what we call a streaming platform. And on top of this streaming platform, we are building a number of services. The main one is the search application. It's the application that serves the search traffic, plus a number of microservices. I'm going to deep dive in Kafka Stream applications to show how it's possible to mitigate the tension between the need to remain decoupled and the need to keep control and combine and enrich data from different services. We think that with this approach, we are not just solving a technical problem, but we are actually simplified developer experience, and more importantly, we think we are enabling experimentation. That is pretty important in a context like the one we work, because basically it's very important for us to create applications to delight our customers in a timely manner. So talking about the context, what is HPC? HPC, Hudson Bay Company, is a Canadian retailer with hundreds of stores, like brick and mortar stores, mainly in North America and Europe. HPC Tech is the company that basically power and improve the user experience of the online banners of HPC. You can see the online banners on the right. Most of you know us as Guild. Guild was one of the banners until 3 months ago. Guild was acquired by HPC in 2016, and the company decided to sell Guild 3 months ago. Most of the content I'm going to show you tonight are coming actually from the experience we have done on Guild, and with this background, we are evolving the HPC architecture as well. So, just to give you an abstract overview of how we evolved the architecture over time, we started in 2007 with a traditional monolith. It was a Ruby on Rails application with Postgres. The business grew and the solution didn't scale, so we decided to go and break up the monolith in large services. We mainly built this using Java. From 2012, we incrementally introduced microservices until we went crazy. I think around 2006, we had more than 300 microservices running in productions. 2016, we kept the work on microservices, and we added also functions as a service. And now we are introducing the streaming platform to share data among services. Well, in fairness, streams is not a new concept for us. I borrowed this slide from a presentation that Aid, our SVP of engineering, gave at the QCon in London here at the Microservices Meetup. Basically, in 2015, we decided to rebuild our search to have what we call a reactive search, so a system where we started from a source of truth that was Postgres. Well, the goal was to basically propagate the changes in Postgres up to a Solr index to serve our search. So to reduce the latency between every change in Postgres until it gets published in Solr. To do this, basically, we started dumping the information we were interested in from the database into S3. So we dumped like brands, products, sales every 6 hours. We create this snapshot. We call it snapshot, and every 6 hours, well, basically we had this new big JSON inside the S3 bucket. In parallel, we built this Calatrava. Calatrava was a simplified version of CDC, change data capture. So every change in the database was propagated in a number of streams that were built on using Kinesis. The core of the system was service search feed. Service search feed had all the logic basically to create new indexes in Solr. And basically it started from the snapshot. When the snapshot was complete, it subscribed to the Kinesis streams to have basically an index in Solr that was up to date with the events. This is what is called the Lambda architecture. This part here is the batch layer, and on the top we have the speed layer, while Solr represents the serving layer. One thing to notice is that we had to introduce what was called a view of truth. That was another Postgres database. Okay, because we started basically from a normalized source of truth, and we had to end up in a denormalized serving layer. And to solve the business rules inside the service search feed, basically this problem was a relational problem. So we decided to keep the data in a local store, so we had more control on the data. A typical example of this is when, for example, a brand change and an event goes through Kinesis. Service search feed in this case had to basically collect all the documents, all the products that were affected by that change to change them in Solr. Without the source of truth, we should have gone back to the main source of truth, and this was not possible. So, as a result, okay, we reached the goal to propagate the change in real time, near real time in Solr. Another nice feature was that we could rebuild indexes with zero downtime, working with alias in Solr. We built this system using Kafka Streams, so the batch layer and the speed layer reuse the same software. We only changed the sources, basically. The problem is that we had to introduce this source of truth that often was cause of slowness because it was a database. We had to optimize it pretty often. Okay, in the past 3 years, we have done a lot of work around Lambda architecture, microservices, and I think that we focused a lot on building engines. What I mean with that is we focused a lot in building internal stuff. All the stuff that you have seen before, it worked at the end, but it's not trivial to build, okay? Well, I think we should, oh, our goal should be to build this, right? What I mean with this is that we should focus more on features that add business value. In the example of search, we should have focused more on search relevance. This is what our users see at the end, okay? So, why Kafka? We think that Kafka, in a number of scenarios, could be a good engine, and we can build on top of it. Anyone here already using Kafka? Okay, I think I can go pretty fast with this. So what is Kafka? Kafka, let's think about Kafka as a distributed file system. The data is structured in topics that then are structured in partitions. Partitions are used for parallelism, basically. The concept is very simple. It's a write-append log. So the producers can only write at the end of the log. Okay? It's immutable, and the consumer can start reading from the beginning until the end. Every record is composed by an offset, and then there is a key and a value. As you can see, I have the same key can appear in the log, okay, at different stages. A really important feature of Kafka that we use often here is the log compaction. Log compaction, basically you can set a topic as log compacted. What it means is that there is a job that from time to when it runs, basically what it does, it removes the old version of the keys. So for example, you will always have the latest version of a given key. In the case of K10, we will see that after the log compactor runs, we only have the record with offset 11, while the previous one was removed. This concept is very, very close to a database table. In a database table, every record, you don't have the history of the records, you have the latest version of the record. And if you think about this, and the example I gave you before with the snapshots and the speed layer, with a solution like Kafka and log compaction, you can remove the batch layer because all your data is log compacted. So you don't need to have a snapshot, start from the snapshot, and then to go back to the speed layer. Everything is a stream there. If you want to create a new index, you just replay the log from the beginning because the log contains the latest version, the version that we are interested in for the search scenario. So Kafka is used widely, and it's used for a number of things. Okay, it's used for as an event pass, as a data store. We are using it as a reactive data processing system, and I'm going to show you tonight how we can use a microservices integration solution. Being very, very basic, at its core, make it very flexible to be used in various contexts. This is partially true because I think that one key aspect of Kafka is the ecosystem. The ecosystem grew in the last 2 years exponentially. We are using a lot Connect to copy data from external sources like databases, S3, Kinesis into Kafka, and then we use sinks to export data from inside Kafka to other systems like Kinesis, like Elasticsearch for our search system. Then there is Kafka Streams. It's the library I'm going to talk in detail in a bit. Schema registry. Schema registry is a very important component, I think. Let's think about it as your API. It's the API for your streams. If you start with Kafka, I advise you to, my suggestion is to start from day one using a schema registry. Basically, you can register your schema for validation purposes. It allows schema evolution, and basically you can store and retrieve schema using Avro. KSQL is one of the newest entry in the Kafka ecosystem. It's basically a SQL engine built on top of Kafka Streams. Basically, it allows you to write streaming applications without programming knowledge with a SQL language. And the last point is Kubernetes operator. This probably would deserve a separate talk because, well, one of the first questions we had when introducing Kafka was, who is gonna be on the hook? Who is gonna be in charge of, you know, all the operational stuff when Kafka goes down? Who is gonna be on the hook? Okay. Well, I have to say that I was a bit worried at the beginning, especially because we have a lot of small teams here. Okay, so we are in charge of the Kafka clusters as well, not just of the application that run on top of Kafka. We started deploying Kafka from day one using Kubernetes, and we are building a number of operators around it. And I have to say that right now we are really confident that even if we are a small team, we can operate Kafka with confidence because everything is monitored. There is an alert for everything. So we are in a really good place in terms of operations. So Kafka Streams. Kafka Streams is a really tiny library. The nice feature is that it's just Java Scala dependency. So you just put it in your Maven, SBT, Gradle. You don't have to set up a cluster because basically all the elasticity, scalability, and fault tolerance is handled in Kafka itself. There is this built-in abstraction that is called stream table duality that I'm going to show you in details in an example. It provides a functional DSL with support for stateless operation like map, filter, aggregations that are stateful like group by or operation to rekey. You can join streams and you can also apply windowing sessions, etc. A really important point for this presentation is it has an internal key value store. This key value store is the one we use is the one that is based on RocksDB, that is an open source Facebook project. And it's used for buffering, aggregations, and interactive queries. This is a really high level of what we are building. So we have Kafka in the middle. It's our streaming platform. We basically push that data into Kafka using connectors, interfacing a number of systems. Then there is our search app that is a Kafka Stream app. I actually simplified this because our search app is composed by a number of stream Kafka Streams app to compose a sort of pipeline. The Stream app basically joins streams, applies business rules, transformations, and then push back the data into derived topics in Kafka that are then pushed in a reactive way into Elasticsearch. But we realized that we can also use Kafka to build our services, our microservices in it. I'm going to show you in the next slides how we can build this WebPDP. WebPDP stands for Product Details Page. Is the service that basically serves the product page. So when you have all the details of a specific product, this service is the service that serves all this stuff. Okay. So, but what is the problem that we are trying to solve here? We are not just introducing Kafka because everybody is using it, right? We have an actual problem, and the problem. To show you the problem, let's go back for a second to the monolith. In the monolith, basically, we have this module inside the monolith that is the WebPDP that talks directly to the database. Okay. In a microservices architecture, we instead have a system like that. We have WebPDP that talks with product service to get product, but the product is not enough for the product detail page. It needs also the availability of the various SKUs of the product. The SKUs are the stock keeping unit. So for an example is a pair of shoes is a product, and the SKUs are the various sizes of that pair of shoes. Okay, so for each one of them you have the availability. I'm not gonna tell you why we switched from the monolith to this approach, because I think everybody here knows it. Okay, there are a lot of advantages in a microservice architecture, like evolving independently. We all know that. But the main problem is that we have lost the freedom of data. And the problem lies in the interfaces. If you think about it, with SQL, basically, we can do whatever we want with data. SQL amplifies the data that is in the database. With SQL, you can have join, you can group by, you can also make computation in database. With REST interfaces, basically, you have lost this, okay? So what usually happens, this basically leads to two anti-patterns. The first one is the God service. It's the service that starts growing, with a lot of functions. It starts looking like a database at the end, with all the problems of a shared database, okay? And the second one is the REST to ETL problem. So when you are building a service, but you prefer to suck all the data and to keep it into your local service for a number of reasons, like aggregation, you have to aggregate with other data, so you prefer to keep it together. The second and probably the most important one is caching. For performance reason, you want to keep the data close to your service. And the third one is ownership. Sometimes you need a change in a service that you depend on, but the team maybe is busy, so they cannot implement the change quick enough. You cannot implement it, so what you do, you read all the data and you start implementing it locally. We are seeing with this that even if we are not breaking the obvious rules of microservices, and our service from a physical point of view are independent, from a logical point of view, they could start looking like a clamp. So to mitigate some of these issues, in the past, we have used caches. Okay, the first take on it was to keep the data on heap. So for WebPDP, WebPDP was a play-scale application. We built a commons library to interface our data services, okay? And there was this product cache. Since this pattern was replicated in a number of services, we decided to build the commons lib. So the commons lib refreshed the data every 20 minutes. The response time was pretty fast because the data was in memory. Unfortunately, the business changed, the catalog grew, and the JSON from product service was around 1 gigabyte. So the start time for this service was around 10 minutes. And the JVM garbage collector went crazy every 20 minutes because it had to remove all the previous cache. And we were spending a fortune because we had like 8 services like this because we need a lot of memory, okay? And if you think that this pattern was not just in this service, but mostly in all our backend for frontend, it's kind of worrying. So we said, okay, we have seen that the Lambda architecture works, so let's try to do something similar, but instead of pushing the data into Solr, we are going to push the data in Elasticache. So it's a centralized cache. We push the data in Elasticache. We remove the big cache inside the commons lib. So startup time, seconds, so pretty good. Second good thing was no more stop the word garbage collection. We we were saving some money with this change, but not much. Why? Because this service needed CPU instances, CPU optimized instances, because it had to marshal a lot of data from Elasticache, and the performance went down because there was a network call, a marshalling. So since performance for product detail page is pretty important, what we ended up doing was adding a small L1 cache. This sounds completely wrong to me and to us actually. So we said this approach doesn't work. So what can we do? Kafka and Kafka Stream. Let's think back about database, okay? We have seen that we cannot go directly to the database anymore, right? But if we think about the components that are inside a database, what are the main components? Well, there is a commit log, there are indexes, caching, and a query engine. Well, we have just listed these features in the features of Kafka and Kafka Streams actually, because our commit log is Kafka. Kafka Stream with the internal state store could represent our indexes and caches, and the state store is queryable. So you can query directly the state store. So let's rewrite our web PDP now. This is the Kafka Stream Scala library. I've used the Scala library. Basically, we are here designing our DAG, directed acyclic graph. What we are doing, well, there is a bit of ceremony here because we are basically saying to Kafka Stream how to serialize and deserialize the data. But what we have in Kafka are, there is an inventory topic with all the inventories. So the keys are the SKU IDs, and the values are, in the value I have the product ID and the availability for each SKU. And then I have a product topic where the key is the product ID and the value is the name, right? When we execute this .table, builder.table inventories and builder.table products, what we do is the so-called stream to table duality. We are going from a stream to a table that is internal inside the application. Okay? So we are creating K tables that are local inside the applications. But what is the problem here? The problem is that this, we want to join this. We want to create something that is called product to reach, that has both the products and inside the products the related SKU. These tables have different IDs, so we cannot join them. To do that, we have to do another step that is called group by. Basically, we are rekeying the inventories. We are basically grouped by the inventory by product key, and we are creating a list of inventories as a value. What we are doing basically is going from this K table where the IDs are the SKUs to this K tables where the IDs are product and the values are list of SKUs. Now we are in the position to join here, to join the products and the inventory and to create our materialized view. That is exactly what we want and is local inside our application. A couple of things to notice is that this operation is stateful. So it means that it creates an internal topic in Kafka, because you can run this process distributed across a number of different nodes. The second thing to notice is this guy called materialized view. I call this materialized view because it actually looks like materialized view in the database jargon. What we are doing is we are pre-computing the data that we want to send back to our clients when it arrives. So we don't need to transform the data anymore when we have to serve the data. The data is already there in the shape that we want. To read the data, simply we get a reference to a store called product reached. That is a key value store, and make a lookup. Simple as it is. The data is already there. It's local. There are no calls to other services. Startup time of this on a single node for our entire product catalog is less than 2 minutes. The response time is really, really fast because the data is already in the shape that we want. There are no dependencies to other services. So that means less things that can go wrong. More importantly, we get also centralized monitoring and alerting because, as I said, we deploy all this stuff in Kubernetes. So every application, every Kafka Stream application that is deployed in Kubernetes gets automatically monitored because what can go wrong here is that the stream process gets stuck and doesn't process events anymore. But this information is in Kafka. So every time we deploy an application there, we get monitoring for free and alerts for free. Because basically what we do is we export the Kafka metrics using a Prometheus exporter. We chart this data on Grafana and we create alerts using Alert Manager of Prometheus. So in summary, we have seen that the Lambda architecture works pretty well, but implementation is not trivial. Stream processing introduces a new paradigm in terms of programming. This is probably an obstacle that we have seen because most of the people are not used to this, and you have to introduce this incrementally. Use schema registry from day one to avoid to break downstream controllers, consumers. And yeah, well, finally, we have seen that a replayable log with a streaming library like Kafka Streams gives us back the control over the data. We can now slice, dice, and enrich and evolve the data locally as much as we want. More or less like we when we had a central database. And at the same time, you increase resilience and performance. A bunch of books, if you are interested in these concepts. The last one is pretty new, and you can download it for free from Confluent. And here there are a bunch of resources, and if you have questions, I hope we have time for some of them. Thank you.